So just in case, what I want to start out with is I want to start out with your end behavior chart. In case you didn't get it to quite to the end, to generalize your end behavior for all polynomial functions. So sometimes we don't graph to find the end behavior and look at it. Sometimes we can just look at the equation that's given and we can determine the end behavior from there. So you'll need 4 different scenarios. And we're going to do it, if you think back and remember to Friday, you were finding the end behavior of a whole bunch of different functions. And what you were supposed to do was come to the conclusion that the leading coefficient being positive or negative and the degree being even or odd impacted what the end behavior looked like. So now we're going to kind of generalize that. So we'll say that this first box is going to be a positive leading coefficient and an even degree. Next one will be a positive leading coefficient and an odd degree. What do you think we do next? Negative leading coefficient and even degree, that's right. And a negative leading coefficient, odd degree. So what we can generalize is that any polynomial, like let's say we're in this very first square, any polynomial that starts with an even number, a positive number, and it has an even degree is going to have the exact same end behavior. So can you think of an easy polynomial that has an even degree? What kind of polynomial has an even degree? Squared. Quadratic, right? What does it look like when we graph a quadratic? Quadratic. Parabola, right? Both ends are going to go the same direction. Do we all agree? They're either both going to go up or both going to go down. What determines if they go up or down? The leading coefficient, the positive or negative. If I start with a positive number, both ends go up, right? Yeah. So that means the limit as x approaches positive infinity of f of x is going to go up. And the limit as x approaches negative infinity of f of x is also going to go up. Both ends are going up, okay? It doesn't matter as long as the leading coefficient is positive and the degree is even, both ends are going to go up. Even if the degree is 24, both ends are going to go up. Y'all with me?
Yep.
All right. Let's go down here. Let's do the opposite of that. So a negative leading coefficient with an even degree, so both ends are going to go down, right? So the limit as x approaches infinity, this time both ends are going to go down. You got a cold, Jackson?
Yeah. Got a foot.
Don't say that. Do you really?
Something like that.
All right. Positive and odd degree. So the easiest thing I can think of is a line.
Yeah.
Right? With a positive slope. The ends are going to go off in opposite directions. Sometimes I have to draw the odd one and look at it so I can kind of remember. Because a line might look like that with a positive slope. Which means to the right, what does the graph do? It goes to the right, it goes up. And how about to the left? Down. How much better that pen's working since I switched this battery around. Last one. So now I'm thinking odd degree, so I'm thinking a line with a negative slope. So it's going to be exactly the opposite. I hope you guys came up with this on your own.
Yeah.
Did you? Did y'all figure it out? Did you? Good. Did we do this chart? I don't think we did the chart. Y'all came up with the chart on your own on that packet, right? I think you did.
Yeah.
But I just want to make sure everybody's on the same page. You got it in your notes. All right, so the right side would go down. Oh, I'm sorry, y'all. And the left side would go up. We're talking about this math. All right, let me give you a polynomial. Tell me the end behavior.
Whoa, 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 whoa.
I'm gonna just put it right up here. Come on. It's not feeling it today.
You jinxed it.
I did. I shouldn't have said anything. I gotta tell you something, Jerome.
That's it.
All I want is you're exactly right, Cameron. I had to look, I heard you, but it didn't register what you said. All I want is the end behavior for this one. So literally all you have to do is look at that first term.
-3.
Negative and even,
It's negative and even. Yeah.
both are going down. Okay? Once you have the chart there, end behavior is a piece of cake without even graphing. I don't have to graph it on my calculator. I don't have to look at it. I can just look at that first term and get the end behavior. Does that make sense to everybody?
Yeah.
Okay. All right, let's do some new stuff. Well, this isn't really new. We're going to keep going with polynomial analysis. Ready, Freddy? Switching gears just a smidge. Let's talk about zeros. We've done zeros of quadratics, where we set them equal to 0 and we solved. So we're still going to pull on those concepts, but now we're going to make it just a little bit more difficult because that's what we do in math. We build. So to do this, we're going to set it equal to 0 and solve. Polynomials being a little bit harder because our degrees are a little bit bigger. Let's say I have. Now graphically, y'all should have this down. How would I find the zeros graphically? Graph it where? On your calculator. And then go second trace and find the zeros. Remember where we did the left bound, right bound, we found the zeros of the function. But if we find it algebraically, this is where we set it equal to 0 and we solve. Oh, I didn't put the... That's exactly right, Cameron. Good job. You can take out an x because remember our goal is to get it into pieces being multiplied together so that we can set each piece equal to 0 to solve. So Cameron said take out an x and she's exactly right. What does it leave when you take out an x?
X squared.
What can I do now?
You put it in order.
You know what I'm about to say?
You gotta add
You
it.
gotta divide by 2.
Factor it. Is that what you were about to say? I thought it was. I thought you didn't print. You got to factor it. This factoring comes back all the time. Okay. So we're going to factor it so that we can hopefully get it in sets of parentheses that are being multiplied together. So tell me what multiplies to -6 but adds to -1.
-3 and 3.
Ooh. You had such confidence with that too, but you were right. That's what you meant to say.
Yeah.
That's what you were trying to say. I knew you were.
You know, it's blue.
Don't say that, Jackson. All right, x squared minus 3x plus 2x. If you're a little rusty on the factoring, you might want to go back and look at that factoring video, yeah. This x is just going to keep carrying down as I go. It's going to stay part of the problem, okay? What can I take out of the first two here? X. What's left? X minus 3. What can I take out of the second two?
2.
2. What's left? Now, to write this, I got an x out front, right? And then I've got an x minus 3. And an x plus 2. Can you solve that now?
Yeah.
Now it's easy to solve. Now everybody goes to what? 0. If x minus 3 equals 0, x equals 3. Now, rewind back to Friday. The degree of the function tells us the most amount of zeros it has, right? So the degree of this function was what? 3. So it told us that the most number of zeros we have are 3, and I have 3, right? What does this look like graphically? These are places where the graph is doing what? Exactly. It's hitting the x-axis. It's either crossing it or sitting on the x-axis, and we're going to talk about in just a second how we can tell the difference. What's the most amount of extrema that this has? Most extrema. What's the most amount of extrema? Maxes and mins. It's n minus 1. So it's the degree minus 1. It's 1 less than the degree. So the most number of extrema it can have is 2. It can have up to 2, but it can't have any more than 2. Does that make sense to everybody? 1 less than the degree. The degree, okay, so the degree of the function tells us how many zeros it can have. But it can't have more than that. So it can't have more than 3 zeros. And 1 less than the degree tells us how many extrema it can have, how many maxes and mins it can have. So it can't have more than 2. And if you think about a cubic that looks something like this, it's not going to have any more than 2. Yeah. Three minus 1. Yeah. Yeah. That's okay. I knew what you meant. What'd you say? Some of it. I got a couple more things to show you. What else was I going to take? Oh, what does the end behavior on this one look like without graphing it? Don't look at this. This might not be right. It's a positive with an odd degree. And that's great. That's the way I want you to think about it. So I'm glad you said that. So you think about a really easy positive odd degree, which would be a line with a positive slope. And what's the end behavior look like? It goes up. Y'all, I'm so impressed. And on the left, it goes down. This is good. This is good. For a minute. This sounds, y'all, the rest of this section uses big words, multiplicity. Oh, nope. God, I sounded it out and everything and still spelled it wrong. What is wrong with me? Multiplicity. Okay. They're big words that sound awful, and when you look at it, you go, oh my gosh, I'll never be able to do that. But they're really easy concepts, okay? Let's say you have something like tell me what this means. What does that mean? If it's cubed, what does that mean? 3 times that factor's in there, right? X minus 2, x minus 2, x minus 2, x plus 1, x plus 1, right? So what this is telling us is this is saying if I found the zeros, right, x minus 2, it's already factored for us. Because this happens 3 times, okay, we say that this is a repeated 0 of multiplicity. All right. 2 is a 0 of multiplicity 3. Where did I get the 3 from? How many times? The multiplicity of 3 just tells me that it happens 3 times. It repeats 3 times. How might I describe the 0 of negative 1?
Negative 1 is 0, multiplicity is 2.
2. Good job. Is a 0 of multiplicity 2. It's going off this exponent. How many times it repeats? Does that make sense? Yes, no, maybe so? It's just wording is all it is. That's all it is.
Why is it Z?
It's 2. I know it.
Kind
No,
of different.
it's 3 times.
Right, right. However many times it repeats.
Okay, so
All right, 2 more things to show you, and that's it. These repeated zeros can be special. Actually, any type of 0 can be special. We have 2 different types of zeros. Can you think of what I might be talking about when I say 2 different types of zeros? Let me draw an example. How many zeros do you have?
3.
Zeros are only where it crosses the x-axis. How many zeros do you have?
2.
2. 1, 2, right? Do you see the difference in the 2? This one crosses all the way through. This one touches and goes back up. You see that? This has an odd multiplicity. Come on. This one, even multiplicity. Now, what do I mean by multiplicity? How many times that multiple is there, right? That factor is there. So that one that I had before, what was that equation I had before? X minus 2 cubed x plus 1 squared. Right? Yeah. This one is going to go all the way through at 2, but at negative 1, and we'll just let this one's pretty close. We'll say this is 1, 2, and this is 1. Do you see what it's doing here? It is, but it's okay. The negative 1, because whenever I solve it, that's giving me the 0. The negative 1 is just touching like that. But the one with the odd is going straight through. Does that make sense to you? Do you see what I'm trying to explain to you?
So if it goes all the way through.
Correct. Odd multiplicity. Let me find an example of one that's going to be. Let's say this was my function. This is going to be, oh no, my fault. All right, here's what I want to do. We're going to do several things with this, and then I still have to show you the intermediate value theorem. All right, I want you to look at this, and I want you to tell me a couple things. First of all, what do you think the degree of this function is?
2.
If you multiplied everything out, This would be a quadratic. You're exactly right, whoever said it over here. This would be a 2, and then you multiply everything, so it would be a power of 3. Yeah, it would be a degree of 3 if you multiplied everything out, okay? Because this would mean I'd have to FOIL it. I'd FOIL it and get a quadratic and then take another one. So it's a degree of 3, which means, what's the name of it? It starts with a C? A cubic. That's exactly right. It's a cubic. What would the end behavior of this cubic look like? The limit as x approaches infinity of f of x would be what? Yeah. Infinity. How about the limit as x approaches negative infinity? If it's an odd degree with a positive leading coefficient. Yes, I am. If you were to multiply that out, Jerome, you would have x times x minus 3 times x minus 3. If I FOILed these two out, I would get x squared minus 3x minus 3x plus 9. I'm really only concerned right now with that very first term. So I would get x to the third. These two become minus 6x. Minus 6x squared plus 9x, if you multiplied it out. I was just looking that I knew this was going to give me a quadratic. I knew that this was a x to the first, so if I took that through, added those exponents, I'd have a cubic. And there's nothing there that's going to cause my leading coefficient to go negative. But if you need to multiply it out and look at it, feel free. What are the zeros? And this is nice because it's already in factored form for us. What are the zeros?
What, 3?
It's 0 and positive 3. What's special about the zeros, though? What about this 3? It's repeated, right? What's the multiplicity? Multiplicity of 2. It's 3 is a 0 of multiplicity 2. Okay, the multiplicity is 2. That's how many times it happens. It's multiplied together twice. Okay. It's repeated. It's a repeated solution. Now let me ask you, of these two zeros, do they both go straight through or sit on the axis? Both of them? Look at this one first. How about this?
Is it even?
Ooh.
Is it even or odd?
Stop. No, it goes straight.
X to the first power. Is one even or odd?
Odd.
Odd. So it goes through. How about this one? This one's even. So it sits on the axis. We're going to do one more thing with this. We're going to sketch it.
How is it even?
2 is an even number, that exponent. Multiplicity 2. 2 is even. How many times it repeats? Where did what one come from? This one? Yeah. Right, because this exponent is odd. If my equation, and I'm coming back to this, if I had had x plus 1 to the third times x plus 2 to the fourth. And maybe I even have an x squared that sits out here. X equals 0. The multiplicity is what? 2. So it's even, so that means it sits on the axis. This one, x equals negative 1, what's the multiplicity? 3, so it's odd, so that means it goes through based on the exponent. So it sits on. Okay. So we're going to sketch what that looks like. right, so let's look at what we know. We know that at 0, it's going through, and at 3, it sits on the axis. I just don't know if it's above the axis or below the axis. So here's what we have to do. We're going to pick points. Actually, we don't even have to do that. Let's don't do that. Let's think about end behavior. What does the end behavior look like here? Both ends are what? Opposite, right? So on this end, it's got to go up. Do you agree? Sorry, when it decides to write. All right, so this end's got to go up. There's no other choice, right? And I know that this is just sitting on it and not going through it. This one is going through and this end's going down. So I don't know exactly how high up this is, but I know that it's going to come through here just as long as I get my zeros right and my end behavior right here. Okay, so without even taking out a graphing calculator, I can determine a lot about this. And whenever we actually graph it, it may end up looking something more like this. Okay, I don't know exactly how extreme those points are right now. I'm not calculating those right now. I just want you to focus on what that multiplicity does to the 0. Does that make sense?
Yeah.
Okay, one more thing and I'm done. Promise. No, but I hadn't done them all yet. Just let me teach. It makes me feel good. Just going to be the never-ending teacher. One more thing, though, for real. Intermediate value theorem. This is another big word. I'm going to give it to you in mathematical terms and then explain to you exactly what it means. If I have two values, if f of A and f of B, so if f of A is less than 0, that means f of A is what? Starts with an N. Negative. Negative is less than 0, right? So f of A, which means the y value when I plug in A. If A, and y'all might have seen this on the SAT this weekend, if the y value is negative when I plug in A, and then I plug in B and I get a positive value, okay? So I've got these two y values. One of them is negative and one of them is positive. And my function is continuous. From the values A to B. Then what that tells me is somewhere between x equals A and x equals B, I don't, but it just fit. This is really, really wordy for a really easy concept, okay? If I have two y values, and think about, we said positive and negative, think about graphically what this means. Y is always positive above the x-axis, and y is always negative below the x-axis, right? So what it's saying is if I have this graph, and somewhere negative, right? F of A is negative. So a y value is negative somewhere. And so this is f of A. and somewhere here it's positive. Okay? I don't care what's happening in between. To get from point A to point B, it has to cross the x-axis somewhere. If it changes from negative to positive, then somewhere in between it has to hit 0. There's no other way to get there but through 0. So that's all it's saying. It's saying is if you have these two, positive and negative, then you have to have a point in the middle where it crosses the x-axis. You have to have a 0. Okay? I want you to think about this for just a minute. If you have an odd-degreed polynomial, what do you know about the end behavior? Every odd-degreed polynomial does what with end behavior? Opposite. Somebody said it. The ends are opposite, right? If you go off in opposite directions every time, either both up or both down, to get to the other side, you've got to cross over x at least once, right? That's why every odd-degreed polynomial has at least one 0. It's got to cross. It doesn't have a choice. To get from positive, negative, or negative, positive, it has to cross. Does that make sense to you?
Yeah.
Okay, it's really wordy, but to get there, it has to cross. All right, I'm going to stop because I've almost lost most of you. Let me tell you what I want you to do. So tomorrow,